Welcome back. This is Mr. Hassan's Maths channel. I'm now answering question number 6 from the October 2023 International A-Level Mechanics M1 paper. And this question here is about vectors. It says, in this question, I and J are horizontal unit vectors directed due east and due north, respectively, and position vectors are given relative to a fixed origin O. So basically, it's like, the vectors vector I is going east, it's horizontal. Vector J is going north. They're 1 unit east and 1 unit north, okay, I and J. And all the vectors are referred to an origin O. When it says position vector, it means from O to the point that they're at. That's what that basically little italic stuff means. It says at 12 o'clock, a ship piece set sail from a harbor with position vector 15I plus 36J kilometers. At 12:30, P is at the point with position vector 20I plus 34J kilometers. Given that P moves with a constant velocity, show that the velocity of P is 10I minus 4J kilometers per hour. So basically, there's a formula that I'm sure you've learned. R equals R0 plus V times T. Now, I don't like people to just parrot and remember formulae. I would like you to understand what it means. So R0 means the place where it was when time was 0, which is 1200 hours. Okay, so they told us that at that time, it was at this position. So R0 is going to be this vector here, 15I plus 36J. Now I'm going to write my vectors as column vectors in my steps and revert back to IJ in my answer if they want us to express it in terms of I and J, because column vectors are way easier to deal with in your calculations. So that's R0. And they told us at 12:30, so we can say R after half an hour, because it's kilometers per hour. So after half an hour, so after at R, you can say when T is 0.5 is going to be at this point 20I. So 20I and 34J, 20, 34. That's what it's going to be after half an hour. That's what it was at the start. That's what it was after half an hour. We want to find what is the velocity vector that took it from there to there in half an hour. Okay, what was its velocity? So if we just look at this, we can see exactly in terms of the formula what we can do. The R is a place where we are at after half an hour. R0 is where we started. V is what we're trying to find, and T is half an hour. So we have T equals 0.5, and V is what we're trying to find. So if I just replace everything in this formula, you have R, which is going to be where we are after half an hour, which is 2034, equals R0, which is the place where we started from, which is 15 and 36, plus V times T, so it's plus 0.5 times the vector V, and that's what we have to find. So if we rearrange this, we have 20, 34 minus 15, 36 equals 0.5 V. And if we just solve this, let me write this a bit neater. 20 minus 15 is going to be 5. And 34 minus 36 is going to be minus 2. And that's equal to 0.5 V. So therefore V, which is the velocity, is going to be, you have to multiply by 2 to get rid of the 0.5. So you multiply that side by 2. It's going to be 10 and minus 4. So we can see that the velocity vector that we're looking for is exactly that, 10I minus 4J kilometers per hour. Okay, so we've shown that the velocity of P is 10I minus 4J kilometers per hour. All right, so that's how we can deal with this. If I just make a little diagram to illustrate something. So this is O. This is the origin to which everything is referred. 1536. This is where the ship was. This is where the harbor is, H. Okay, so this is the vector that takes you from the origin to the harbor. Okay, that's 1536. That's where the ship was at time equals 0. Okay, that's like, this is, you could say R0. And the ship was half an hour later at 2034. So 2034, somewhere like over here. All right, so the ship was at this point sometime later. Okay, this is its position after half an hour. Okay, which was 2034. Okay, 2034. So it moved like this in this direction in half an hour. Okay, so velocity is measured, kilometers per hour. So we found this when we subtracted these two, we found this is 5 minus 2, but velocity is measured per hour. This is half an hour, so in 1 hour it's going to go twice that distance. So the velocity vector is actually this whole from there to there. That's the velocity vector. That's just half the velocity. So that's the velocity vector, 10I minus 4j. From there to there, that's 10I minus 4j. That's the vector that takes you from here to here. Okay? But the position vector of the point on P, okay, or where P is moving, will be given, okay, by this, which we're going to actually do in part B. I've gone a bit too far here. So actually, I've explained part of what we're going to do. They said at time t hours after 12, the position vector of the particle P is given by P kilometers. So that's what they want us to find. The position vector in terms of vectors, I, J, and T. So as I just mentioned here, this is where it's going to be at 1 hour. Okay? It's going to be, its position will be from O to that point. Okay? So you can say the position vector of P after 1 hour is going to be R0 plus its velocity times 1. Okay, so we're going to use this vector R equals R0 plus VT to find the actual position vector. Okay, so we know R0 is where it was when time is 0 in the beginning, which is 1536. We know that its velocity vector now, we found the velocity vector is 10 negative 4. We were told to actually show that. So we already know that as well. And T is just the general value of T. We want to find the general expression for P for any time T. So we can say P is going to be R0, which is 1536, where it started from, plus T times 10 minus 4. Okay, so plus T times 10 minus 4. So after 1 hour, when T is 1, it's going to be at this point over here. At 2 hours, it's going to be at this point over here. At 1.5 hours, it's going to be at that point over here. So the position vector after 1 hour will be 1536 plus 1 times the velocity. After 1.5 hours, it will be 1536 plus 2 times the velocity vector. After 2 hours, plus 1.5 times the velocity vector, sorry. After 3 hours, it will be the 1536 plus 3 times the velocity vector. So the value of T will tell you exactly where you are. So we can now rewrite this in the form that they want. I'll write this first as 15 plus 10 Ti and 36 minus 4 times Tj. So we can say in the form that they want, you have 15 plus 10 Ti plus 36 minus 4 Tj. And that's kilometers. That's the position vector of P at any given time T. Okay, I like to use it in this form. All right, that's how you should write the answer in this question, because they said in terms of I, J, and T. You could also write it, if you want, alternatively as 15 I plus 36 J plus T times 10I minus 4J. That's the same as this, like 15I plus 36J plus T times 10I minus 4J. Okay, you can write it in either of these two forms. Okay, that would be fine. I like to have it in this form written down because I like to calculate using it in this form. Okay, so that is the position vector of P. And that's part B finished. Now for part C. It says the second ship is also traveling at constant velocity. At time t hours after 12, the position vector of Q is given by Q, the vector Q, which is this. Now I'm going to rewrite Q as, I'll rewrite it over here. I'll rewrite it as 42 minus 8ti, 9 plus 14tj. And our vector P from the last page, if we remember, was 15 plus 10ti, 15 plus 10, 36 minus 4. 15 plus 10, so we had 15 plus 10t and 36 minus 4t. Let's make sure again, in case I don't want to make a mistake. Yep, that's fine. Okay, so that is our vector P and our vector Q. That's the position vector of P at any time t. And there's another ship, which is Q, which is, it's got a position vector given by this So they're both moving at certain speeds and in certain directions. Okay, and they're telling us here, if both ships maintain their course, first of all, verify that they would collide at 13:30. So they're both starting at the same time, 12 o'clock, right? So at 13:30, the time would be 1.5 hours. So we have to verify that after 1.5 hours, they collide. So we can do this in a couple of ways. We can say, where will P be after 1.5 hours? It's going to be 15 plus 10 times 1.5 and 36 minus 4 times 1.5. That's where it's going to be, which is 15 plus 15, which is 30, 36 minus 6, which is also 30. So P at 1.5 hours, its position with relation to the origin will be 30, 30. Okay, let's see what happens to Q at 1.5 hours. It's going to be at the point 42 minus 8 times 1.5 and 9 plus 14 times 1.5. So that's 42 minus, that's 8 plus 4, 12. 42 minus 12. And you're going to have 9 plus, that's going to be 14 plus 7, 21. And lo and behold, you can see 42 minus 12 is 30. And 9 plus 21 is also 30. So at T equals 1.5 hours, P and Q will be at the same place exactly. At the same place. Okay? Which is 30, 30. 30, 30. Therefore, they would collide, if they carried on the same course, they would collide at 14, what was it? At 13:30. 13:30, or sorry, 1.5 hours after they started. They would collide at 13:30. So that's a nice, easy way of doing this. We could have also done it by equating the I components, and we would have got T equals 30. Okay, no, we would have got T equals 1.5. Okay, and equating the J components, we would have also got T equals 1.5. If they both give us the same value of T, okay, then that would be the value of T at which they collide, which would be showing that, right? So if I did 15 plus 10T equals 42 minus 8T, equate the I components. That gives me 18T equals, this side, 18T equals 42 minus 15, which is 27. So T is equal to 27 over 18, which is 1.5, 3 over 2, 1.5. And if we equate the J components, we can say that 36 minus 4 times T equals 9 plus 14T. So we're going to have 36 minus 9, which is 27, equals 14 plus 4, which is 18T. So again, we'll have 27 over 18, which is also 1.5. They both give us the same time, 1.5. So they both, I and J components will be the same at 1.5 hours, so they will collide. But I think this is a nicer way. Just find where they are at that time. And if they both give you exactly the same position vector at that time, they must collide at that time. Okay? So that's killing two birds with one stone. So they will collide at 13:30. And the second thing is, what will be the position vector of the point at which they collide? We'll give it in terms of R. So the position vector of the point where they collide is going to be 30I plus 30J kilometers. Okay, because that's part 1, we verified that they collide. Part 2, we gave the position vector of where they collide. And that completes this question number 6, part C. And now we're going to go on to part D. Now for part D. This is at 12:30, Q changes speed and direction to avoid the collision. Ship Q now travels due north with a constant speed of 15 kilometers per hour. Ship P maintains the same constant velocity throughout. Find the exact distance between P and Q at 14:30. So let's deal with P first, because P didn't change its velocity. So P, okay, it's going on this course, 15 plus 10T, 36 minus 4T for the whole time. Okay, so from 1200 hours when they started until 1430, okay, where we have to find what the distance between the two ships are, which is time equals 2.5 hours. It's going on this course. So we can say at 1430, the position vector of P is going to be 15 plus 10 times 2.5 over I, and 36 minus 4 times 2.5 J, which is going to be 15 plus 25, which is 40, and 36 minus 10, which is 26. So that's the position vector of P at 2.5 hours. 2.5, that's where it is. So 40, 26. Okay, so we know where P is at that time. Okay, as for Q, and I won't put this as 2.5, I'll put this is going to be P at the time 1430. Okay, P at the time 1430. As for Q, okay, Q is going to go until 1230 at that. So Q is going to go on this course 42 minus 8 times T, I, and 9 plus 14 TJ, okay, until time equals 1230. Okay, so that's going to be for 0.5 hours. Okay, so this is until 1230. So T equals 0.5 hours. It's going to go along this course. Okay, so we can say T at the time 1230 is going to be 42 minus 8 times 0.5 I, and 9 plus 14 times 0.5 J. So that's going to be 42 minus 4, which is 38, and 9 plus 7, which is 16. So that's the position of Q, not at 1230, not at 230, sorry, but at 1230. Okay, we want to know where Q is at 230. Okay, we want to know where they are at the same time. But Q now, at this point, it changes course. Okay, so the new position vector of Q, all right, let's call it Q dash, which starts at 1230, is going to be its initial position vector, which is where it's starting from. Its new course starts from this point here, 3816. That's where this is like the R0. This is where it's starting from now, plus T. I'll put T dash because it's a different T now from the original T that we had. Okay, and it's going due north with a constant speed of 15 kilometers per hour. So the velocity vector of this is, the velocity of vector P dash is going to be due north, so 0 horizontally and 15 straight up, 0, 15. That's going to be its velocity vector now. So this is going to be 0, 15 is its velocity vector. And we want to find where Q is at 1430. Okay, so where Q is at 1430. Okay, we know where it is at 1230. So it's going to be 1430, and this is 1230. This is where it is at 1230. So that's 2 hours. So we put T equals 2, okay, into here, and it will be Q at 1430. Okay, and that's where Q will be. So we have 38 plus 2 times 0, which is 0, 0, and 16 plus 2 times 15, which is 30. So we end up at 38 and 46. Okay, 38 and 46. Of course, you see the I component stayed the same because it's going due north. And the J component is going to be 30 more because it's going up for 2 hours, 15 kilometers per hour. So now we can see that the position vector of P at 1430 is what we found, 4026. And the position vector of Q at 1430 is 38 and 46. So now we need to find the magnitude of the vector between them. So if we subtract these two vectors, like just imagine if you want to just picture what we're doing now, we have, just imagine we have the vector, what am I doing? 1 second. Supposing this is the origin. Okay. The vector P is 20, 40, 26. 40, 26. Somewhere over there. So that's P. And vector Q from here is 38, a bit less, 46, a bit more. That's Q. All right. So this is the vector OP. This is the vector OQ. So I'll just put it like this. This is a vector P, and this is a vector Q. Okay. This is the vector Q. So this is the vector P, the vector Q at 12:30. Okay. Now this vector here is the vector that takes us from this point to that point, which is going to be the vector Q minus P, you could say. Q minus P, that will take us from there to there. We want to find the magnitude of that vector. We want to find the distance between them. We want to find what that vector is and the magnitude of that vector. And that will give us what we're looking for, the distance between them at that time. Okay, so basically we take these vectors, find the magnitude of Q minus P, and that will be our answer. So that's going to be the magnitude of 38, 46 minus 40, 26, which is going to be the magnitude of the vector. 38 minus 40 is minus 2, and 46 minus 26 is 20. So we're going to find the magnitude of this vector, which is found by the square root of 2 squared plus 200 squared, 20 squared, that's 400. So it's the square root of 404, which will be, I think, 2 times the square root of 101, right? Let's just make sure. We have the square root of 404, 2 root 101, and it says in exact form, exact distance, so we don't round it to 3SF or anything. We leave it like that, so we can say that the distance required is 2 times the square root of 101 kilometers. And there's the answer to part D of this question. I hope that was clear. Other questions from this particular paper can be found in the playlist over here. They're linked over here. The link at the end of the video over here will take you to my playlist of M1 vectors at Edexcel. Other questions, if you would like to subscribe to my channel, you can click on this link, and if you'd like to watch a video that tells you how to use my channel to find what you're looking for, click on the link over there. Thank you for watching, and see you soon.